Concrete does not merely dominate the construction industry. It is the concrete industry, in a way that no other material has ever dominated any other sector of the built environment. It is embedded in every building code on the planet. The structural calculations that determine how thick a wall must be, how deep a foundation must run, and how wide a bridge deck must span are calibrated around concrete's specific properties and have been for over a century. It is embedded in every engineering curriculum so that every structural engineer trained in the last 100 years has learned to think in concrete, first, and ask about alternatives second. It is embedded in every supply chain, the quarries, the grinding mills, the batch plants, the ready-mix trucks, the pump systems, a global industrial infrastructure worth trillions of dollars that exists for one purpose and cannot be repurposed overnight. The carbon problem inside this system is not a side effect of how concrete is made. It is a consequence of what concrete requires. Cement, the binding agent that gives concrete its structural properties, is produced by heating limestone to 1,400 degrees Celsius in a rotary kiln. At that temperature, calcium carbonate in the limestone breaks down into calcium oxide and carbon dioxide. This reaction is called calcination. The carbon dioxide it releases is not combustion waste. It is not the exhaust of a dirty power source that could be replaced with a renewable one. It is a direct molecular output of the chemical transformation that makes cement possible. Approximately 60% of cement's total carbon emissions come from calcination alone, regardless of what fuel powers the kiln or how efficiently the facility operates. The remaining 40% comes from burning fossil fuels to reach the required temperature, a portion that cleaner energy can theoretically address. The 60% cannot be addressed by an energy transition at all. Global cement production currently stands at approximately 4 billion tons per year, generating roughly 2.9 billion tons of CO2 annually from calcination alone. The industry did not ignore this. Research institutions, engineering schools, and climate bodies spent decades cataloging alternatives. Geopolymer cements, binders made from industrial waste products like fly ash and slag, were identified as a promising path in the 1970s and remain promising today, with a global market share of less than 2%. Supplementary cementitious materials, partial replacements for clinker in the cement blend, have been adopted widely, but hit a ceiling determined by structural performance requirements that conventional building codes will not bend. Carbon capture, retrofitted to cement kilns, has been piloted at significant expense and remains economically unviable at scale in every competitive construction market on Earth. By the early 2020s, the industry's collective position was not denial. It was something more uncomfortable than denial. It was structural resignation, the acknowledgement that the problem was real, the paths were insufficient, and demand was not slowing down. Global cement consumption is projected to grow by 12 to 23% by 2050 as South and Southeast Asia continue urbanizing at rates the developed world has not seen since the mid-20th century. The lock system was not shrinking, it was expanding. The research coalition that changed this did not emerge from the institutions that had been working longest on the problem. It was not a European cement company with decades of carbon capture investment, not a North American materials science consortium backed by Climate Foundation grants, not a United Nations industrial transition program. It was a coordinated, multi-institution effort spanning Tongji University, the China Building Materials Academy, and Shanghai Jiao Tong University, three institutions with overlapping but distinct technical competencies, whose collaboration on this specific question appears to have been deliberate rather than incidental, and whose combined resources included industrial-scale hydraulic pressing equipment that most university research facilities in the world do not possess. The prevailing research direction in construction materials science at the time was focused logically enough on the ingredients. If the carbon problem is in the limestone, change what you use instead of limestone. If the durability problem is in the water to cement ratio, develop chemical admixtures that allow lower ratios without sacrificing workability. If the structural ceiling is in the aggregate bond, develop new surface treatments that improve adhesion at the microscopic level. These were reasonable questions pursued by serious researchers, and they had produced incremental gains over 4 decades without producing a result that restructured the economics of the material at scale. The Tongji CBMA-SJTU team approached the problem from a different angle. Not the ingredients, not the chemistry, not the binding mechanism. They asked instead what happens to concrete in the 30 seconds after it leaves the mixer, the window during which fresh concrete is still a plastic, workable material whose final microstructure has not yet been determined by the hardening process. In that window, the mix contains excess water beyond what the hydration reaction actually requires, and it contains trapped air introduced during mixing. Both are structural liabilities. Excess water, as it migrates out during curing, leaves behind a network of capillary pores. Trapped air remains as voids. Both reduce density, reduce strength, and create pathways for water, chlorides, and other agents of long-term deterioration to enter the hardened material over decades of service life. The team's hypothesis was straightforward. If you could mechanically remove those liabilities before the concrete hardened, the material you were left with would be fundamentally denser and stronger than anything the same ingredients could produce under conventional curing. They published the results under a fully open license, raw data sets, microscope imaging, and nanomechanical test results made available to any research institution or engineering body that wanted to examine them, at a moment when the industry's default posture toward process innovation was proprietary lockdown. The process is called compression casting. Fresh concrete, mixed to standard specifications using standard cement, standard aggregate, and standard water, is placed into a hydraulic press and subjected to between 5 and 15 megapascals of applied pressure while still in its plastic state. 1 megapascal is approximately 145 pounds per square inch. The pressures used in compression casting are, at the upper range, equivalent to the force at the bottom of a column of water 1.5 kilometers deep. Applied to wet concrete, that force does two things simultaneously. First, it expels excess water and trapped air, the two structural liabilities the Tongji CBMA-SJTU team had identified as the primary sources of long-term weakness, are driven out of the mix under pressure. What remains is a denser, more uniform matrix with a substantially lower water to cement ratio than the mix started with, achieved not by reducing the water added during mixing, but by removing it mechanically after mixing, a distinction with significant practical consequences for workability and placement. Second, it collapses. The interfacial transition zone, the boundary layer between cement paste and stone aggregate, is historically the weakest point in any concrete structure. Under standard curing conditions, this zone has a higher void content than either the paste or the aggregate on their own, because water films form around aggregate particles during mixing and impede the tight packing of cement grains at the contact surface. Under compression, those voids collapse. The team's measurements showed a 35% reduction in void content at the transition zone compared to equivalent standard cured concrete. Total internal porosity across the sample fell by 45%. The consequences cascade. A 45% reduction in porosity does not produce a 45% increase in compressive strength. The relationship between density and strength in concrete is nonlinear. At the highest pressure ranges tested, compressive strength increased by over 80% relative to identically proportioned standard concrete. Resistance to water intrusion improved substantially. Resistance to freeze-thaw cycling, the mechanism responsible for a significant share of infrastructure deterioration in cold climates, improved. Resistance to chloride penetration, the process by which dissolved salts migrate through concrete and initiate corrosion of steel reinforcement from the inside outward, improved to a degree that projected service life extensions measured in decades rather than years. Same cement, same stone, same water, different handling. Engineers in Germany, Japan, and South Korea responded by filing patent families and initiating highway trials before the ink on the published datasets had finished drying. The laboratory results were, by any measure, exceptional. An 80% compressive strength gain from a process change requiring no new materials is not the kind of result that appears in peer-reviewed construction engineering literature without attracting immediate and intense scrutiny, which is precisely why the Research Coalition did not ask the engineering community to take the laboratory results on faith. They built a bridge. The Jiang River Trial, 150 meters of bridge deck, constructed using compression cast concrete and instrumented throughout with continuous strain gauges and moisture sensors, was not a controlled laboratory environment. It was a working structure, subjected to live traffic loads, seasonal temperature variation, and the full range of environmental stresses that determine whether a material performs in the real world the way it performs under controlled conditions. The sensors embedded in the deck were not there to make the structure more interesting. They were there to generate a continuous, publicly available record of in-service performance that any engineer anywhere could examine independently. Over 12 months of monitored service, the bridge deck delivered an average in-service compressive strength of 61 megapascals. The laboratory models had predicted 61 megapascals. The match was not approximate. It was exact. Or as exact as measurement precision in civil engineering field conditions permits, which is a different and more meaningful standard than laboratory precision, because it incorporates every source of real-world variability that laboratory conditions exclude by design. Zero visible cracking was recorded across the full observation period. Moisture sensor readings remained stable throughout, indicating that no water intrusion pathway had developed in the hardened concrete matrix despite 12 months of cyclic loading and environmental exposure. What the Jiang trial produced was not a press release. It was independently verifiable field evidence, a data set available to any research institution or government engineering body that wished to replicate the analysis, stress test the conclusions, or use the performance record as the basis for regulatory review. The global engineering community had been handed not a claim but a proof, documented in a format designed to withstand the scrutiny of the most demanding technical audiences in the world. Research teams in Germany had already begun highway trials using compression cast prefabricated elements. Japanese infrastructure planners had begun regulatory review. South Korean engineering firms had begun integrating the process into smart city pilot programs. The field evidence had arrived, and it had matched the laboratory predictions with a precision that left the skeptical case with very little to stand on. Compression casting makes concrete significantly better. What Broad Group built makes concrete significantly less necessary. BCor is a structural panel system developed by Broad Group, a Chinese construction technology company whose previous work had already established a track record of building at speeds that conventional construction timelines treat as physically implausible. The panel's architecture is straightforward to describe and difficult to fully appreciate without seeing the load data. Two thin steel skins, outer faces that provide the structural surface, are separated by a geometric lattice of hollow tubes engineered to tolerances more commonly associated with aerospace manufacturing than civil construction. The result is a panel that weighs less than 1/10 of a reinforced concrete slab of equivalent dimensions while carrying equivalent structural loads. Not comparable loads. Not loads within an acceptable engineering margin. Equivalent loads, verified under standardized testing conditions. The assembly system that delivers BCor panels to a building site uses robotic fasteners, connection hardware designed with the same philosophy as the panels themselves, which is that every variable the engineering process can eliminate, it should eliminate, because every variable is a source of delay, error, and cost. The consequence of this philosophy was demonstrated in Chengdu in 2025, when a 10-story building was completed in under 30 hours. Not a prefabricated show structure for an expo audience. A building, 10 stories, 30 hours. The speed was not a product of workers moving faster. It was a product of a system engineered for assembly, the way aircraft fuselages are engineered for strength to weight. Every component designed to connect to every other component with a minimum of adjustment and a maximum of precision, so that the act of construction becomes closer to the act of assembly than to the act of building in the traditional sense. The seismic performance data adds a dimension that moves BCor from impressive to strategically significant. In earthquake load testing conducted under conditions corresponding to the seismic risk profiles of the most densely populated construction zones on Earth across East Asia, South Asia, and the Western Americas, BCor structural frames outperformed conventional reinforced concrete frames. For the countries where earthquake resilience is not a premium feature but a baseline construction requirement, this is not a marginal improvement. It is a different risk equation entirely. BCor does not compete with compression cast concrete. In structural applications where it is deployed, it removes the need for concrete columns and load-bearing walls almost entirely, which means the question of what happens when both technologies operate in the same construction environment is not a theoretical one. When compression casting and BCor operate together in the same construction environment, the effects on cement consumption, carbon output, construction time, and post-installation maintenance cost do not add. They multiply. Here is the honest picture. BCor panels carry structural loads that would otherwise be carried by reinforced concrete columns and walls. Wherever a BCor panel replaces a concrete structural element, that concrete is not produced more efficiently. It is not produced at all. The cement that would have been required to manufacture it, the water, the aggregate, the carbon embedded in the calcination reaction, the transport cost, the on-site placement time, all of it is removed from the project's balance sheet simultaneously. In a mixed BCor and compression cast concrete building, the portions of the structure that still require concrete benefit from a 40% reduction in cement consumption per cubic meter at equivalent compressive strength, because compression casting achieves higher density with less binding material. The portions that do not require concrete have been replaced entirely. Construction time compresses from both directions. BCor's assembly speed reduces the time required to raise the structural frame. Compression cast concrete elements, produced as prefabricated components under controlled industrial conditions, arrive on site already cured to their full design strength, eliminating the multi-week waiting periods that on-site poured concrete imposes on every subsequent stage of the construction schedule. A project that would take 18 months under conventional methods does not take 12 months under the combined system. It takes less because the time savings are not sequential, they are concurrent. Post-installation maintenance costs shift on a longer timeline, but by a larger magnitude. Compression cast concrete's 45% reduction in porosity translates directly into reduced chloride penetration rates, reduced freeze-thaw deterioration, and reduced water intrusion. The three primary mechanisms of concrete infrastructure decay in the climates where the largest share of global construction takes place. Structures that would require significant remediation at 25 years of service life now project to reach 40 or 50 years without equivalent intervention. The reduction in lifetime maintenance cost per structure, aggregated across the volume of infrastructure being built in developing economies over the next 3 decades, is not a rounding error. It is a number that changes the long-term economics of public infrastructure finance. This is not a story about greener concrete. It is a story about who restructures, the fundamental economics of the substance that holds up the built world and who does not. To understand why China developed these technologies, it is necessary to understand the scale at which China builds. Between 2011 and 2013, a single 2-year window, China consumed more cement than the United States consumed across the entire 20th century. Not more per year. More in total. Every highway, every dam, every skyscraper, every public housing block, every industrial facility constructed in the United States between 1900 and 2000 required less cement than China used in 24 months. China did not develop compression casting and BCor from an environmentalist position. It developed them from the position of the world's largest builder, confronting simultaneously the world's largest carbon liability, the world's most acute pressure to reduce construction costs, and the world's most urgent need to build faster than conventional methods allow. The open license under which the compression casting research was published was not an act of scientific generosity in tension with China's strategic interests. It was consistent with them. The research was published with full datasets, raw results, and nanomechanical imaging at a moment when 34 international patent families covering compression casting process variations, equipment configurations, and application-specific implementations had already been filed. The blueprints were made available to the world. The mechanisms required to implement those blueprints at industrial scale, such as the pressing equipment, the process control systems, and the prefabrication infrastructure, are manufactured, exported, and licensed primarily by Chinese companies. The export data makes the export position concrete in the most literal sense. Chinese carbon-cured concrete additive exports to the United States, the United Kingdom, and Southeast Asia increased 5-fold in the 2 years following the open publication of the compression casting research. Beijing Cement Group signed a 5-year licensing agreement with Lafarge Holcim, the world's largest cement manufacturer, covering prefabricated compression cast construction for the European market. Obayashi Corporation, one of Japan's largest construction companies, entered a joint research program. Berlin highway authorities began field trials of compression cast road panels manufactured using Chinese process equipment. Hyundai Engineering's Smart City division in South Korea integrated BCor panels into its flagship pilot program. Osaka Expo infrastructure planners specified compression cast prefabricated elements for permanent structures across the exhibition site. China handed the world the blueprints. It positioned its own manufacturers, exporters, and licensors at the center of every supply chain required to build with them. What looks from a distance like a contribution to global decarbonization is, at closer range, a structural insertion into the next generation of construction technology at planetary scale. This is the precise moment when the world's building codes, infrastructure programs, and construction companies have no viable alternative to engaging with it. Life cycle models developed by construction engineering research groups in Europe and East Asia project that applying compression casting to just 30% of new global structural concrete, not all concrete, not even most concrete, just 30%, would eliminate approximately 850 million tons of carbon dioxide annually. The Germany comparison is the one that makes that number land with the weight it deserves. 850 million tons is more than the entire national greenhouse gas emissions of Germany, from every source combined, every car, every factory, every power plant, every agricultural operation, every heated building across one of the largest industrial economies in Europe, eliminated each year, not by replacing Germany's energy system, but by changing what happens to wet concrete in the 30 seconds after it leaves the mixer, applied to less than a third of the concrete being poured. The framing of this as a climate story is incomplete. In any construction market that has implemented carbon pricing, and the number of those markets is not shrinking. The cost advantage of 40% less cement per cubic meter, combined with 80% higher compressive strength, is not a trend that construction companies will choose to adopt when the conditions are right. It is a competitive reality they cannot afford to ignore when a competitor has already adopted it. The carbon benefit and the cost benefit point in the same direction. Carbon pricing makes the cost advantage larger, not smaller, as the price of emitting carbon dioxide rises. The adoption argument is not a climate argument dressed in economics. It is an economics argument that happens to produce a climate outcome. China has not positioned itself to benefit from this transition when it arrives. It is already inside it, as manufacturer of the pressing equipment, as licensor of the process patents, as exporter of the additive compounds, as standard setter in the prefabricated construction systems that the world's largest infrastructure programs are beginning to specify. The moment when global building codes are being rewritten, when construction companies in Europe and East Asia are selecting the technical standards their supply chains will align to for the next 30 years, is not approaching. It is now. And the entity that arrived at that moment as manufacturer, licensor, exporter, and standard setter was not late. The question for every construction market outside China is not whether these technologies will restructure how the world builds. The structural and economic evidence has already settled that. The question is whether those markets will write their own standards, or whether the standards will simply arrive already written, already embedded in the supply chains they depend on, already set.